In this video, we're going to use octave to understand how the dynamic response of a mass spring system changes as we change the parameters and the initial conditions in an interactive way. So we've seen before how to construct the response of such a system using the solution of the differential equation of the dynamics. Based on this script, we're going to include a few things so we can interactively change the values of these parameters or the initial conditions and see how this response changes. In order to do that, we're going to use a function in Octave which is the keyboard hit. So I'll just show how this function works. This is the function we're going to use, kbHit, and we call it like this. And when we call it, Octave is gonna wait for us to press something on the keyboard, and if we press something, it will say which key is pressed. So we can put that in a variable, for example, key, and again we run it, and it will wait for us to press some key. I'll press letter A, and now the variable key has the value A. It has a character A as its value. So here's our variable key, and this is its value. So we can see what the user is typing if we use this simple function here. And we can use that so we can change the values for parameters and initial conditions. So the idea here is to use this function kbHit, and whenever the user or you press a key, we can, for example, change the value of the mass, recalculate our response, and update this response and the figure that is open. So let's start on building on this idea. First I will rename this file, as we're doing something a bit more elaborated. We need to put this plot as a object, as we've done in previous videos, so we can change it later. So that's the first change we're going to make. Second, we need to, after we have plotted our first response, we need to wait for the user to do something. So we usually do that inside a while loop. So a while loop, as it's written here, while 1, it will just stay running forever until you press something or do some command for it to stop. And inside this while loop, we're going to ask, or we're going to use that function kbHit to see if the user is pressing something. Remember that when we issue this command kbHit, Octave stops everything and waits for until something is pressed on the keyboard. If something is pressed on the keyboard, we need to do something with it. So first we need to understand, or we need to find out what key was pressed. So we can use, for example, the switch structure, which you might have seen before in some computer programming course. And we're going to ask what is this value that is stored in the variable key. And we can use the switch case structure then and see if, for example, the user pressed the letter A or the key A. We're going to do something. We're going to say, for example, display a message. Or we're going to do something more interesting later, but we can start just to check our code, something like this. That would be the simplest way of using the switch case function. We also need an AND to end the switch. But in Octave we can, before finishing it, we can use the otherwise. So we will have a bunch of cases and we end with an otherwise we do something else here to finish our while loop, for example. So we say, for example, if we press any other key that we're not using the cases beforehand, we will break the while loop and it will get out of the loop. So let's see what happens if we run this code like this. Before we run, let's just put a message as well here so we know that we are exiting the while loop. Something like that. So I'll go on and run this this script. So it calculated our responses and plotted the figure, and now we need to go to the command window so we can press something and see what is going on. So remember, we have to before we go on, I'll just include a message here to say that we are leaving the while loop, just we know that we are in the right place. So I'll go on and run this script. So Octave already calculated the response, plotted figure, and now we want to see what is going on, if this structure here is working alright. For that we need to go here in the command window so we can press something and Octave can read it. So remember, we have two options right now. We can press A, or we can press any other key and leave the while loop. So I'll just press any other key apart from A, and it displays the message, and you see that it goes back to the prompt, so the while loop is ended. So let's go on and do something more interesting with this structure. So let's say when we press the letter A, we want to increase the mass of our system by some amount, and we're going to recalculate our response and update our figure with the new response. And if we do that, we can repeat this structure for all the other parameters as well. So let's start with that. Let's try to change the value of m, recalculate the displacement x, and update our figure. So the first thing we need then is to see by how much we're going to change our parameter. So let's say we can increase m by 10%, something like this. And we can call this increase that we have here some step, for example. And we can define this step previously here in the parameters for our script. So I'll do it like this. I'll say that every time we press a key, we're going to change the parameter by 10%. And that is what is going to happen here. If we press letter A, the new value of m will be 10% higher than the previous value of m. With our new value of m, we need to update our value of omega n, because it will be a different value as m changes. And with omega n, we can now recalculate the response. I'll just copy and paste down here. We can recalculate the response x, because as we change m and that incurred a change in omega n, our x is going to change accordingly. Now we can update our plot, which shows our response related to time, and we can use that command we used before, the set command, to update some object, the object that we are calling, that we are storing here for the plot, and this variable p1. So I'm going to update the p1, specifically the x data property of this object, and I'm just going to put the new value of x there. Well, sorry, it's not the x data property. We're going to change the displacement x is stored in the vertical axis of our object, so it's y data that we're going to change. So let's go on and see what happens when we run this script. So Octave calculated the first response with these values that we coded here before, and it shows us the figure here with these parameters. And now it is in this while loop waiting for us to press something and interact with the figure. Again, we need to go to the command window so we can, so Octave can actually see what we are pressing. So the idea is that if we press the A letter in the keyboard, the value of mass is going to increase, and we can see the new response according to that. So that's what I'm doing here. I'm increasing the mass and updating the figure, and we see that as we increase the mass, the system responds in a slower fashion, so it takes longer to complete one oscillation. But you can see that the amplitude of oscillation doesn't change. So that's something, that's what is happening with an increase in the mass. Let's try to do a bit more complete script so we can increase and decrease the mass. So first I'm going to get out of here by pressing any other key apart from A, so I'm pressing something else here, and we left. So great, so far everything is working as planned. So let's go back to the editor and see, we have a case here that when we press the letter A, we would increase our value of mass and update everything according to that. Now let's add another case here, and let's see if we press another key, for example Z, just because it's below A, we're going to do something else. We're going to decrease the value of mass. So I'm going to do M over step. So I'm going to decrease it by, in this case, 10%. And after that, I'm going to update the value of omega n, the values of the response x, and the figure the same way as I've done before. So I'm just going to copy these 3 lines and paste it here after I decrease the value of m. So here we go, we already have 2 cases. We can increase the value of mass by pressing A and decrease the value of mass by pressing Z. If we press anything other than A or Z, we're going to leave our while loop. So let's see how that works out. Again, Octave plot the first response, and it is waiting for us to interact with the script. Again, we need to go to the command window, and we can press A to increase our mass, and if we press Z, we decrease our mass like so. And if we press anything else, we get out of the loop. So that's great. We can change the value of mass. We can increase and decrease it to see what happens to our system. Let's do similar things to the other parameter k. So I'll just copy and paste these 2 cases because they're going to be very similar for the parameter k. So as we want to include more cases, we can just do like so. We can keep pasting more cases here inside this switch structure before the otherwise. So let's say now that if we press S or X on the keyboard, we're going to increase or decrease the value of k. So for example, if we press S, we're going to change the value of k, we're going to increase it. Again, we're using that same step variable, so we are going to increase it by 10%. As we change the value of k, we need to update our omega n, and we update the response x, and we update the figure. Again, we're going to do the same thing or similar when we want to decrease the value of k, the stiffness of our spring, when we press x. So we're going to say that k is going to decrease, so I'm going to over by step, so I'm gonna decrease by 10%. Again, I'm going to update omega n, update the response x, and update the plot using the set command here. As we are onto it, I'm going to increase more for cases, so we can increase and decrease both initial conditions here. So initial condition for displacement and initial condition for velocity. So let's start doing that. I'll include another case here. So let's use the letters D and C. I'm just going sequentially on my keyboard here. Say when we press the letter D, I'm going to increase my initial condition by a small amount, like that. And see that when we change the initial condition, we don't have to worry about omega n, because that's not going to change. We just need to worry about updating our response x and updating our plot that is stored in the object p1. So that's what I do to increase my initial condition for displacement, and now keep copying and pasting to include the other cases. So now I'm going to include the case for decreasing my initial condition. I'm going to use the letter C for that. So the only thing that is going to change is that instead of plus, I'm going to use minus a small value. So we just included a case for increasing displacement, initial condition for displacement, and another case for decreasing initial condition for displacement. So I'm going to copy and paste these last two cases and do something similar for the initial condition for velocity, what we call x0d. So I'm going to copy and paste, and we keep increasing our switch structure with all the cases that we want to use. So again, going again on my keyboard, I'm going to use letter F so we can increase the condition for velocity, and letter V for decreasing my initial condition for velocity. So there we go, we have all the cases that we need to change the mass, to change the stiffness, to change initial condition for displacement, and to change the initial condition for velocity. And again, we need to find the condition or the structure here in the otherwise space, so we can exit our while loop, which is the outermost structure here, just waiting for our interaction with the keyboard. I'll put a few more things in our figure, which is for us to see in our figure what is the value of the parameters that we have, because now we can change everything in our system. It's interesting so we can keep track of them, so we can see the values, the actual values in the screen as well. So we can create more objects in our figure using the function text, which will place a piece of text in some position on the screen. And this position we give here in coordinates. So for example, I'm going to give at the coordinate 0 for x and minus 1.8 for y, I'm going to put a piece of text that shows us the value of the mass. And for that I'm going to use this function which transforms a value which is stored here in this variable m. So this is a value, it's not a string, and I'm going to convert that to a string and show that in the screen for us. So I'm going to do that for all the other parameter and initial conditions that I'm changing. So I'm going to do that for parameter k, and I'm going to do that for the initial condition for velocity x0, and also for the initial condition for this is for displacement, and this is for velocity x0 d. So now we have our whole script. We have our initial calculation of the response with these values that we coded here. We show the values in the script in the screen as well, and then we go into our while loop, waiting for us to interact with this with the system, so we can change the parameters and initial conditions. Now one more thing, I actually made a mistake here because I'm putting all the text one on top of the other. I'm using the same coordinates for all of them. We need to use different coordinates, so for example I'll just scatter them along the horizontal line so they don't stay on top of each other. Now we can run this script and start interacting with it to see how everything is working. So again, we need to go here on the command window so we can interact with it. So we see here the values of our parameters and initial conditions, and I can press A, for example, to increase two more things we need to include here. I actually put all the tags one on top of the other. I'm using the same coordinates for them, so that's not nice. Let's scatter them around an horizontal line, something like this, so they don't stay on top of each other. And another thing is that when we change the values, we need to update these texts as well. So we need to do something like a set command, and we update the object that contains the value of the text we want, and the property that we're going to change is the string of this text, and we're going to use this same function that we used here to convert a numeric value to a string, and so we can update our text on the screen. So we need to put that into all the other cases as well. So again, for increasing and decreasing the mass, for increasing and decreasing our stiffness K. So here's for decreasing it, and here is for increasing and decreasing our initial condition for displacement, and here for the decreasing, and finally for the increasing and decreasing of x0 dot, so our initial condition for velocity. So that's it. With these modifications, we're finally ready to run our script. So I'll go on and run it. So again, Octave calculated the first response with the coded values for m and k and the initial conditions, and now it is waiting for us to interact with the script. So again, we need to go to the command window so we can press keys on the keyboard and it understands what we're doing. So you see that now it shows here the values of mass, stiffness, and the initial conditions for displacement and velocity. So we can go and change, for example, the mass. We can increase the mass, see what's going on. So we saw that with the increase of mass, the system responds a bit slower. and if we decrease the mass to the initial value, it goes back to the same period of oscillation. We can keep decreasing to make the system even faster, and go back to the initial value of 10. With the stiffness, if we increase the stiffness like that, we see that the system tends to oscillate faster. So it is the inverse of the characteristic of the mass. So with higher stiffness, the system responds faster, and with lower stiffness, if we go back to 100, we see that the system responds slower, and we can keep decreasing the stiffness to see something like that. Now let's see what happens with the initial condition for displacement. Actually, we change the amplitude, as we see here. So if we keep increasing this initial condition, we see that the point where the system starts oscillating changes, and with it the amplitude of oscillation will change, and it will keep oscillating with this amplitude that we set here for the initial condition. And if we decrease it, we see something similar happens. And we see that we can decrease this initial condition to below 0, and that will see as if we actually push the mass against the spring and release it from there. So the response is similar, but just the opposite. It's just starts in the negative value, but it keeps oscillating with this amplitude like so. So we can go back to that initial displacement of 1. Now finally we can change the initial condition of velocity. So if we increase it, you see that the initial slope here in our response will change as we increase or decrease the initial condition for velocity. So that's the effect of it. It will change this initial slope here in our response. We can increase it and we can decrease it to change this slope here. So that's it. Now we have a interactive way of seeing the changes that we have in the response of this dynamical system here in the background as we change the parameters and as we change the initial condition.